class. So today is first practice class. And we try to do something together today. So I ask you please to try to participate to this practice.
Scusi, ma si sente malissimo.
Si sente malissimo. Adesso meglio.
Sì, sì, adesso meglio.
Allora, tolgo il microfono se parlo solo dal cellulare. Allora, so now we start with the first exercise, which is a very simple one. We try to make we talked about throwing stones and calculating the thrust generated by throwing stones. And what we can do is start with, let's say, a toy rifle, una pistola a giocattolo. And with this toy, we eject balls of 0.1 grams each. At the speed, these balls are ejected at a speed of 100 meters per second. And we deliver 4 balls per second. So the question is, what will be the thrust generated by such a gun if we consider there are no other forces, just this one in an ideal environment? We just would like to evaluate what will be the thrust. So you do the exercise, not myself. I already did. No?
Questa è 2 o
Sì. Pressione della spinta. You have just to use what you know about the thrust. Very simple. Cos'è che turba? So we have to be able to apply what we learn different kind of application. We have to be flexible. What is mass flow rate?
La portata in massa per la velocità d'uscita.
So the analogous of the mass flow rate, the mass ejected per unit time, will be the mass of the single ball by the number of balls ejected per unit time. So we have, this is the frequency, this is 1/2 second, so we have 0.4 grams per second. And then, of course, we have this velocity. This would be our ejection velocity. And it will result. I wait some of you that tell me what is this thrust.
0,04.
Exactly. So this is the force that we have realized. This was the first exercise. Next one. This time I would like to evaluate the force exerted by a jet over a wall. Imagine something like this. So you can see here, jet exhausting, for instance, from a rocket. And let's suppose that the rocket is just at zero velocity, just lifting off. And we have that the velocity of this jet is UE equal to 2,800 meters per second. And the mass flow rate of this ejection is 100 kilograms per second. So what we have to do is we have a jet impinging on the floor, on the ground here, so which is a generic wall, and this jet hit towards a given velocity, and then, at least in this direction, in the vertical direction, loses entirely its momentum. So this means that there is a force acting on the ground. Are you able to evaluate it? So the topic of this practice class is the use of the balance of forces and momentum, and of course of the expression of thrust in next exercises. We will see something also about specific impulse and so on. Is it clear to you? Also, who are listening on remote. I hope everybody is trying to get the answer. And if text is not clear of this exercise, I will repeat.
Is it possible to repeat, please?
Yes. We have a jet hitting the ground, and this jet is characterized by given mass flow rate and exospeed. So we have a jet with this mass flow rate and exospeed hitting the ground. Our question is, there will be a force on the ground. What is this force? How much? How many Newton I will find on the ground? So of course, as usual, if I have this pen or something else in my hand and I leave it and I throw it towards the ground, so I give to it a momentum, I throw it towards the ground, this momentum will be lost by the pen. Once it reaches the ground, it will be stopped. So to change this momentum, there will be a force exchanged by this pen and the ground. And this is the same happens with a jet. So this jet has some momentum, but hitting on the ground, of course, it will go, of course, in the other direction, because mass cannot vanish. But momentum in the vertical direction will be completely lost. It means that a force will be acting on this jet to make it change completely its velocity in the vertical direction. Come on, it's very simple. It's exactly the truth, because we have mass flow rate, velocity, momentum. But it's clear the reason why this force here is exactly the one that we have given. We have provided a momentum to this mass flow rate through the engine, and we do the opposite, going down up to zero, the same mass flow rate here, and so we have the opposite force. Something changes if you consider now that this rocket is moving at this time when we have this jet on the ground, is moving at a velocity of 100 kilometers per hour. Let's consider the jet remains not disturbed by the environment, so it reaches, even if this rocket is moving, it reaches the ground. So also this is quite simple. Exactly. So this time we have to consider what will be the velocity of the jet hitting the ground.
Professore,
Sì.
noi almeno da remoto non stiamo proprio capendo l'audio.
Non sentite, quindi, più che non capite.
Sì.
Adesso?
Penso un po'
Meglio così. Sì, purtroppo sono col cellulare perché la parte audio qui per qualche motivo non funziona mai. Vabbè, comunque, spero che adesso mi sentiate.
Sì, così è meglio.
Faccio una prova, Per caso così sentite? No, perché la cuffia. Ho fatto una prova, ma
Sì, così sì.
sicuramente adesso sì, come prima. Va bene. I hope you have followed this exercise, at least what we have changed now. So the first part of the exercise was to compute the force on the ground with the rocket standing at zero velocity. So we have that the force is exactly equal and opposite to the thrust we have provided to this jet. The same force, an equal force, must be exerted to the jet to bring it at zero velocity. In the second case, we are considering now that the rocket is moving at a speed of 100 kilometers per hour. So in this case, some of your colleagues suggested that we should consider the relative velocity of the jet with respect to the ground. But you have to do this carefully. So it's easy, don't worry. I'm sure you're doing it correctly. So as first, I wait a number coming from your calculations, and then we will discuss.
Is it 277 kilonewtons?
More or less. Yes. Should be okay. So what we have to do, why I say that we have to be careful with the relative velocity, because of course it's not only the velocity, but it's also the mass flow rate that reaches the ground that is less than in the former case. And this is because it's moving, it's moving vertically, this rocket, and so some less mass will reach per unit time the ground. So of course, in this case, we should consider that F is equal to, let's say, dot m prime UE prime, where this dot m prime is equal to, of course, density, velocity, area, but this time of course, the relative velocity. So here we can consider rho UE A Q E prime UE and we can write in this way to take into account the change of velocity. And here our line will be UE minus B. And this will be 2272.2 meters per second, just making the conversion between kilometers per hour and meters per second. And so the mass flow rate is now 99 kilograms per second, something less. At the end, this was the result given by your colleague. My calculations lead to 274.4 newtons. So another, if you are okay with this, We can move to another one. Which is the following. We consider now a rocket operating in adapted conditions. That means that we have no pressure term, just the impulsive term of the thrust. Is operating in adapted conditions at an altitude of 10 kilometers. So we have that when z is equal to 10 kilometers, we have that PA is equal to 26.5 kilopascal. And at this altitude, we have that PE equal to PA, and as a consequence, not as a consequence. And we have here that thrust is equal to 1 meganewton or 1000 kilonewton. We also know that the exit area is 2.5 square meters. So it's a big engine. So the question is, can you evaluate thrust at sea level? Can you evaluate thrust in vacuum? So this is even simpler than the other exercises. So of course here it's just make an operation. Just we have everything. This is a direct problem. It's just what the pressure term and make the evaluation. We have the area, we have the pressure, almost everything. So we can call this PA 10 kilometers. And of course, we assume that PA vacuum means that it's about 0. So this is the expression of pressure, and this here, the exit pressure is exactly PA 10 kilometers. So in vacuum we have just the first term, and at sea level we have just to make this operation. So what we see is that there is a little difference between the thrust at 10 kilometers and the thrust in vacuum. That will be greater than, of course, the thrust at that altitude, because we have this additional expansion up to the vacuum condition. And so we have here one 0.66.2 kilonewtons, and here at sea level, instead we have to pay the fact that we are in an overexpanded condition, so we expand more than possible because of the atmosphere, and so our jet will be slowed down by the atmosphere up to it recover the ambient pressure. So we have, and there is a greater difference between these pressures here. So we have a greater difference, 8.6.2 kilonewtons. And we see that we have a decreasing force with the ambient pressure, a linear decrease. We see it in this expression. We have a fixed value. This will be fixed values, the adapted thrust, and the exit pressure, the exit area. If the ambient pressure is changing, we are decreasing the value of thrust linearly, of course, with a negative slope as shown by this minus sign, this expression. Okay, this was too easy, right? So we can go ahead. Let's see the next one. We raise a little bit the difficulty, but not too much. So now we have a rocket realizing a specific impulse in vacuum of, so right here, ISP vacuum is equal to 434 seconds. We know also that at sea level, we have a specific impulse of of 318 seconds. So of course, sea level means pressure 100 kilopascal. Now, knowing that TE, the exit pressure, is equal to 20 kilopascal, now I would like to compute the exhaust velocity of the engine, so the jet velocity at the exit of the engine. Or we can also read this as the specific impulse at the adaptation altitude is the same as the exhaust velocity of the jet in this one-dimensional model. So there was a question, I just was able to read it now, about the previous exercise about the force of gravity on the rocket. Of course, this is a force acting on the rocket, but not on the jet hitting the ground. So the question was relevant to the problem of the jet hitting the ground, and of course the gravity force will be on the rocket. We don't see the role of gravity force on the jet. News is a bad news or a good news?
Potrebbe essere 4025 metri al secondo?
Potrebbe essere, sì. Grosso modo ci siamo. Qualche dipende ovviamente dal valore di G0 che ho usato, può venire qualche piccola differenza. So we have a news and we can proceed at this point. We just have to write the expression of trust and specific impact for two cases that where we know the specific impact. So we can write that in general this is a specific impulse expressed in terms of velocity, and this will be the exit velocity plus P minus PA multiplying AE divided by dot M, mass flow rate. And you can write this at the two conditions that we know. So in practice, we have here U AQ SL is equal to UE plus PE minus PA SL AE over dot M. And this in case of vacuum. So we know here these two terms. We know the pressure terms, and we have two equations, and the two unknowns are AE over dot M and UE. Two equations, two unknowns, we can solve. The system, we can, as we are interested in UE, we can eliminate AE over dot M, and we find the solution. So actually, we can consider here UQ SL minus UE over specific impulse at vacuum minus exit velocity, like this difference, and this will be the ratio PE minus PA SL over PE. And so this point is just algebra that allow us to write the, for instance, that UE equal to EQ vacuum minus PE over PA by the difference of the two impulse we know. Okay, this is, of course, you can move in different ways. You can replace, make a substitution as you like. At the end, this is what we obtain. Of course, we have to consider now a value of G0, for instance, that can be 8 and 9.81 or 9.80665, depends on how many you would like to bring with you. And we have that solution. If I take 9.81, the solution is 4,029.9 meters per second, corresponding to a specific impulse in adapted condition of 410.8 seconds. Let's do also this further exercise before the break because it's very quick. This time we would like to compare the consumption, let's say the propellant consumption of an air breathing engine and of a rocket operating in adapted conditions. Both operating in adapted conditions, and that both devices produce the same thrust at zero velocity. So we have a turbojet and a rocket. We have V equal to 0. We have F turbojet equal to F rocket, adapted condition. And exo speed is UE TJ, turbojet is 700 meters per second, and UE rocket is 4,000 meters per second. So what we know is that for the turbojet, we have that the fuel mass flow rate is 2% of the air mass flow rate that is used. Well, so we have this can be written as Fm dot A, and F is equal to 2%. So with this, we like to understand what of the two devices consumes more propellant. We would like to make a comparison. The ratio of the two consumption, for instance, how much the ratio between the rocket propellant consumption and the turbojet propellant consumption. So I don't want to spend much time on this exercise. So just the expression of thrust, if we have V equal to 0 and adapted condition is the same for rocket and turbojet. It's just mass flow rate by exhaust velocity. The difference is that, of course, you have for the turbojet, you have to consider the whole mass flow rate, including and fuel. For the rocket, the whole propellant mass flow rate. But at the end, what we have to compare is the fuel mass flow rate for the turbojet and the propellant mass flow rate for the rocket. So in principle, for the same thrust, we should have less mass flow rate for the rocket. So it seems to be, of course, less, but as turbojet consumes also air, actually, even if we have a lower exhaust speed, there will be less consumption for air breathing engine. So we can write that Tj is equal to dot me Tj ue Tj and Fr is equal dot me r e r. But what we like to evaluate is the ratio dot p, let's call it dot p over dot m. So we can here try to express, to make in this ratio appear, can simplify. It would be convenient to consider dot mp over dot me turbojet. This is dot mp, and dot me turbojet over dot mf. So that here we have the inverse ratio of exhaust velocities, because we have the same F. So here we have Tj over R. And then we have this ratio exit over, we have this ratio me Tj over mf, and this will be mf plus ma over mf. I divide everything by ma, so it will be 1 plus f over f. And this is what I have to place here. And this is the final result, is 8.925. So I think we can make a break of 5 minutes and resume shortly. Okay, I think we can start and continue with the next exercise. In this case, we would like to realize a thrust of 5,000 kilonewton. And we have available different kinds of rocket engines. In particular, we have a first set available, which is made of engines having a thrust of 1,000 kilonewton and a specific impulse of 380 seconds. Then we have a second family of thrust, or better, rockets, giving a thrust of 2,000 kilonewton. And a specific impulse, 260 seconds. And finally, we have a third kind of engines able to generate 2,500 kilonewtons with a specific impulse of 320 seconds. So we have to see, you have to imagine that we have available on the market this kind of rockets, and like consider the different combinations that allow us to get 5,000 kilonewton. And for each of the possible combination, you have to evaluate the resulting specific impulse. Can you? No. Can you hear me? Mi sentite?
Sì, sì.
Okay. So we have two trivial solutions, as I mentioned, by 5 rockets of kind A or 2 rockets of kind C. More interesting are other possible combinations. No, semplicemente valutare qual è l'impulso specifico. Io non so se sappiamo qual è l'impulso specifico delle diverse combinazioni di propulsori. So the goal of the exercise is also to see what is the resulting specific impulse given by a combination of rockets having different specific impulse each. So also here, I think this is very simple, but this start to be important. Because this is something we cannot fail. It's one of the kind of operation that we are not allowed to fail. That means knowing what's meaning of specific, knowing how to handle it when we have different engines with different specific impulses operating together. This is something happening, for instance, for case of parallel staging, as we will see. So let's try to make it shorter. For the first case, what will be the specific impulse? For the first case I mentioned, I mean, when we have select 5 engines of kind A, what would be the specific impulse of this combination of rockets? Yes, of course. Don't try to see something different. to say something different. If I consider equal engines, I will have the same specific impulse. We have not to sum the specific impulse. We have not to multiply the specific impulse. We have 5 times the thrust, 5 times the mass flow rate, but the same specific impulse for the engine. Each engine is providing here same specific impulse. So, and the same is true also if you consider 2 engines of kind C. So let's find another combination. We have to get 5,000. Here we can take, for instance, 2 engines of kind B and 1 A, or 3A and 1B. So let's try to do one of them. Quale?
2B più A.
Uh, 2B più 1A, you say 237 seconds. Is correct. So let's try to see how to do it. So we have that the specific impulse has this definition. So here what we have to consider is the overall mass flow rate that we obtain considering 2 engines of kind B and 1 of kind A. So we have that dot M, let's say B, is FB as this expression, and dot M A, of course, it's a similar expression. So if I substitute here, this 2B and 1A. The thrust will be 2 times thrust B plus thrust of the engine A, and the mass flow rate will be 2 times the mass flow rate of the engine B and one time and of course divided everything by G0 because I have that time G0 so that I will cancel this G0 again. And so at this point we can just to get the result because we know the value of the different quantities and well, this is we can use the numbers. Okay. And then G0 will simplify here, so we have so FB is 2000 divided by 260 plus FA is 1000 divided by 380. And this should be 277.5 seconds. In the other case, the result is 20.8 seconds. Should be 1 of kind B and 3A. We have you can check if this is the correct result. Okay. Yes. So. Now, let's consider our box that we have seen in class. It's a box with a hole here, and we have filled this box with air at 4 bar. So we can remove a closure here on the back and get a mass flow rate of 1 gram per second. We assume that with this velocity of the jet, with this rate of emptying of the box, the temperature of the air inside the box will not change, will remain constant and equal to the room temperature, which is 20 degrees Celsius. So the question is, we should evaluate the time along with the duration of the thrust that we can generate with this box, with this hole. So how long it will take to empty the box. we make the assumption that the mass flow rate is 1 gram per second that we have at the beginning. The mass flow rate will change according to the pressure that we have within the box. So there is a direct relation between mass flow rate and pressure in the box. And then we know that we are working with air, so we have a molar mass of air that we can assume as 29 kilograms per kilomole. And the universal gas constant is, of course, the usual one. Let's take this value. So with this information, we'd like to evaluate how long it will take to reach zero thrust, let's say, for this box.
Professore, scusi, potrebbe gentilmente ripetere la relazione tra il flusso di massa e la pressione all'interno che non si è sentito a tratti?
Proporzionalità diretta. Is a constant and P0.
Ok, grazie.
Prego. So I apologize. You are trying to solve something that cannot be solved because I missed one information. The volume is 1 liter. So with the available volume, we can evaluate the initial mass. This R is the gas constant. And so we have that M is equal to P V R T and we can compute this initial mass that is equal to 4.76 grams. And you have also final mass. Of course, the pressure will not be 0, will be atmospheric pressure at the end. And so we can find that this is 1.19 grams. So to evaluate the time, we can see the rate of decrease of mass inside the box, and in particular, we can say that the change of mass will be given by a decrease of mass inside, and is related, of course, to the mass flow rate of the jet that we know is proportional to pressure. So we can evaluate this dot M, and we can say that is proportional to pressure. Now, if you look to this relation of the masses, at the generic time, we have that m is equal to p v over r is 0. So we can also say, if we make the ratio mass to this one, we see that is equal, or looking on the other direction, we see that P over P0 is also equal to M0. So we can replace here and write that dm is equal to minus dot m is dot M0 over M0 m dt. And at this point, we have a differential equation that can be easily integrated. So we have that the logarithm of m is equal to minus dot M0 over M0 dt. This is a constant, of course, and finally we obtain we obtain that, of course, time 0 is 0 and M0 is the mass initial time is no. So we obtain that T is equal to M0 over dot M0 logarithm of initial to the final mass, or to the initial to the final pressure is the same. Is 6.6 seconds. Consider that if you assume constant, erroneously constant mass flow rate, of course, you don't take into account the decrease of mass flow rate as pressure decreases, and so you should we would obtain a shorter time, 3.6 seconds. So let's consider a final exercise for today now. This final exercise is the following. Then I have also another one, but I think, or another two, but I leave this for the next practice, or I will leave you on the learning. So here we'll do the following. We have to consider a vehicle with 5 rocket engines and with an amount of propellant on board equal to 700% of the initial rocket. So we have something like rocket you have 5 engines. And we have that the propellant mass is 70% of the overall mass. Each rocket provides the same thrust and the same specific impulse that we assume do not change in time. So we have constant thrust, constant specific impulse for each of the 5 engines that we have. And we assume the first question is, let's assume that ISP is equal to 260 seconds. And the question is, what is the maximum time it can last to consume all the propellant, provided that the thrust allows to lift the rocket? So we have to generate a thrust that is able to lift the rocket, and depending on this thrust level, of course, the consumption can be, the use of propellant can be more or less faster, and so we have less long time. We have to try to compute the maximum time we spend to consume the whole amount of propellant. The maximum time means the minimum thrust to lift off the rocket. If you accelerate more, you have a higher force, and of course you will have a higher rate of consumption of propellant, and so the time will be shorter. But as a reference, we consider that we have to lift off this rocket. So we try to find the maximum time, and so the time that will last to consume the whole amount of propellant. With just this information is enough. The information, these two informations, that the propellant mass is 700% of the initial mass and the specific impulse is 260 seconds. So as the thrust is related to the mass of the vehicle from one end, and to the mass flow rate on the other end, there will be some kind of simplification that allow us to make computation just with this information. So here the subscript is the number of engines. So for instance, F5 means 5 times F1, which is the thrust generated by a single engine, and that M5 is 5 times that M1. This alpha, you that if the thrust is equal to that M0 G0, you have the thrust is equal to the weight, and so we have the minimum, let's say, this plus epsilon allow us to lift off in theory. This alpha is a multiplier, and we see, of course, that if we are going to get maximum time, this alpha should be the minimum. That means 1. If alpha is greater than 1, it means that we have a higher acceleration at liftoff. And then the time is just what will be propellant mass divided by propellant mass per rate. We make substitution and we obtain the result. So first I replace this term phi, and then I replace here the expression on the basis of the initial weight and so we see here that alpha should be the minimum to get to time, and so alpha is equal to 1. The minimum alpha must be greater than 1 to lift off. So at the end, we have here 0.7 by 260. The result is 182 seconds. We have to stop here, but I just would like to list a number of other questions that comes to complete this exercise. And the second part is related to the failure of one of the engines. Let's suppose that one of the engines fails after 10 seconds. So in this case, how long will it take to consume the whole amount of propellant? Moreover, if this happens at the time when we have this failure, is the force generated by this cluster of greater than the weight? Of course, weight is changing as we move propellant. So after 10 seconds, we have consumed part of the propellant. The weight of the vehicle will be, but this will be also lower because there is failure of one engine. So we have 4/5 of the initial thrust, 4/5. So we have to make this check. If the answer is no, and the answer will be no, we can evaluate what is the minimum time we have to allow for an engine failure. So what will be the minimum time that have to be sure that we have all the thrust greater than the weight of the rocket? And also, alternatively, or let's say, we assume that we have to admit a failure after 10 seconds. What should be the value of alpha, the thrust level we need to guarantee that at 10 seconds we have enough thrust to balance the weight? So you will find these questions are already available, I think, except the last, are already available in the text in the e-learning, and I will add this last question as soon as I can. And then I can stop here today's practice. I hope that can be considered at least a little bit useful. We started with something quite simple, but this helps us to let's say, to review what we have seen in class in terms of thrust, of force and momentum balance, and of thrust specific impulse definition.